Next speaker is Matt Kumjian. Matt is an associate professor at the Department of Meteorology and Atmospheric Science at Penn State. His interests are in using polarimetric radar observations and numerical modeling to understand microphysical processes in storms. And he will speak to us about using ARM polarimetric Doppler radar observations to inform particle property predicting bulk ice microphysics schemes. Matt, take it away.
All right, thank you very much. I think I am unmuted here, so go ahead and get started. So I'd like to thank my collaborators on this project, Robert Shrum, former student of mine who's now at NASA, Marcus Van der Welke, Jerry Harrington at Penn State, Lee Donovan, former student at Penn State who is now at Sims and OU, and new student Sarah Gott at Penn State, and then Anders Jensen, now a former Penn Stater who's now at NCAR. So I'm going to shift gears a little bit and talk about snow and ice microphysics now, but using some of the same ideas that were led in by Hugh and Carly. So as Sam gave a nice overview of the importance of clouds to our climate system in terms of the radiative balance and the cloud aerosol interaction uncertainties. And to kind of motivate this a little bit is a picture from NASA of some clouds. And clouds are located across the globe quite often, as you all know. But if we were to kind of fly an aircraft into these clouds or try to sample these clouds, we might notice a variety of different types of ice particles and ice crystal shapes that may arise. And these different shapes arise from different microphysical processes that are happening inside that cloud. But the key is that these different shapes are going to change the way in which these particles then scatter or absorb radiation, both from the sun and the long-wave radiation from the Earth. As well as even governing through feedbacks the life cycles of the clouds and some of the clouds' microphysical properties as well. So it's really important to try to understand and characterize these different shapes when we are simulating these processes in cloud models and climate models. So unfortunately, many of these cloud models and cloud parameterizations, as Hugh was talking about, have a lot of inherent uncertainties associated with our lack of knowledge. A new class of these types of models that we're starting to move to is what are known as particle property models. And basically these particle property models just predict hydrometeor properties, including aspect ratio, density, size, etc. And so as the means of an example, if we started out with some small sort of spherical ice particle, one of these models would tell how under the influence of some process such as vapor diffusional growth, that particle will elongate or change in its shape, maybe making an oblate spheroid. And I've kind of made it a little bit less dense looking here with the grayish shading. So these models will track in bulk these types of properties as the clouds evolve. So these particle property model parameterizations themselves are in parts informed by laboratory measurements. So for example, if some laboratory measurements, and I've taken this figure from Jerry Harrington et al.'s paper in 2013, but these laboratory measurements come from far earlier than that. But basically, if you were to track the growth of this semi-axis along the basal face of the ice crystal for 15 minutes of growth at different temperatures, you might see a pattern that looks something like this. And there have been a few different attempts at parameterizing this so-called inherent growth ratio, or the ratio of these different axis lengths between the A-axis and the C-axis, which would be along the prism face, which are shown by these markers and shown by these sort of parameterizations here. So you can see that they're a large function of temperature, but there's also some spread or some shadings between these two curves, just kind of represents some means of the uncertainty there. And as well as you can see that the data points from the laboratory measurements, we don't have error bars on them, but there are error bars there as well. And so there's definitely uncertainty both in the laboratory measurements that are informing these particle property models as well as those parameterizations themselves. So we're going to be focusing on a very narrow range, just right here centered on about -15 degrees Celsius, where you see a very large difference between the A-axis growth after 15 minutes and the C-axis growth, which would lead to very flat plate-like crystals and some branch planar crystals, dendrites, and things like that. So we have these particle property models, and the idea here is we want to try to use some sort of observations to constrain them. And obviously, being a radar person, I always kind of think of radar first, but ARM is also in the radar business as well and has a lot of observations from around the world. In particular, the polarimetric radar observations, the results that you get, the signals you get, do depend on the hydrometeor properties like aspect ratio, density, and size of those particles. And those line up very well with what the particle property models are predicting. And in particular, as Carly was just showing, for rain, the same thing happens in snow, where we can look at profiles of these measurements to try to tell us something about how those particle properties are changing as they descend towards the ground, and thus something about those microphysical process rates themselves. So with all that, the challenge becomes, can we use these radar observations to constrain our model? And we can always constrain a model with observations. It doesn't mean we do a good job at it. So maybe a more sort of significant challenge here would be, can we do so robustly, quantitatively, and in a way that respects the inherent uncertainties involved? And we heard a little bit about those uncertainties from the previous two talks. So as the previous two talks suggested, we're also going to be using Bayesian inference here, looking at the MCMC framework to answer this question. So I figured I would kind of pose this problem as an overview of the different sort of challenges or the different types of things to consider when trying to constrain our models with observations, because it turns out every turn is a little bit more challenging than you might have expected at first. So the first question is basically, which observations should we use? So for this particular case, if we were focused only on the vapor depositional growth, that narrowed it down quite a bit to these cases where we have no significant aggregation, no significant riming or melting. So just focus on the vapor growth of ice crystals. So we found some observations from the Arctic. This is from the X-SAPR radar. And as you can see in these different panels, this top one here is reflectivity, which, as Carly said, is kind of proportional to the size of the particles. The middle one is the ZDR, which is dependent on the shape of the particles. And then this bottom panel shows the elevation angle. And I put all these up just because we had to think about a little bit the geometry of the radar as it's scanning. These plots are sort of vertical cross sections through the precipitation. So you can see they're in ground distance versus altitude with the radar at the center here. And what you do notice is that in the ZDR field, the sort of apparent shape that we're getting from the scattering information changes with elevation angle. And that's just because of the geometry of how you're viewing the crystals. If they fall with their large axis predominantly in the horizontal, as you look at them from angles that are increasingly looking up, you eventually see them from below. And that kind of looks like it has its symmetry. So you kind of lose that shape information. Further, if you look at the spatial field of the precipitation, you see that it's not homogeneous. And this is pretty standard if you look at any sort of clouds. You're going to see spatial heterogeneities, temporal heterogeneities. And so the idea is, how do we pick observations that would be appropriate to use in this type of framework? So to do this, we started by doing some spatial averaging, which are kind of shown by these boxes here. And we also constrained ourselves to kind of just looking at the initial growth, because we sort of see there's some sort of fall streak that's the precipitation is falling out of the view of the radar for this one. So we're going to only focus on the upper several hundred meters for these observations. We also have an additional radar co-located at that site in the north slope of Alaska, which is the KZR. It's a Ka band radar. This one is vertically pointing. So basically it just sits there and stares up as the snow moves overhead. And so we have reflectivity, which is kind of proportional to the particle sizes and concentrations. And then the bottom one here is actually showing a measure of the radial velocity, with the motion of those particles towards or away from the radar, which gives us some information about their fall speeds. And that's important because those fall speeds are going to be proportional to the mass of the particles as well. And so again, here we're left with this kind of uncertainty in where do we choose our observational point, or which times or heights do we choose for our observations. You can see little generating cells and fall streaks going through here. So obviously the choice is not just to sort of throw the radar data into the MCMC framework. We need to sort of be selective and try to respect the uncertainties that arise from this choice. So what we did was we did some temporal averaging for this one, and for this particular radar. So once we get our observations, the next question is, how do we represent the environment of the parent cloud and the environments and the parent cloud dynamics as well? And we could do very realistic modeling, say with a large eddy simulation, but as Carly said, using a few 100,000 or a few million MCMC runs, that would not be feasible. So we wanted to stick with a really simplistic model that just basically captured some essence of the cloud dynamics we might be seeing. So this is showing the simulated flow and precipitation fields, the flow field on the left and the precipitation ice in this kind of shaded area here. And then the environment we used was extracted from a real sounding, which is shown in this kind of white line. And then the model sounding that's sort of produced after the model is run and the little updraft and downdraft cells have their chance to go is shown by this yellow line, with the error bars indicating sort of the spread in the environment that we see. So as you might be thinking to yourself, well, this kind of simple just up and down pattern to the flow is probably not very realistic. And we agree with that. It's definitely an uncertainty and a source of error that we're adding into this framework. But what we can do is treat it as an uncertain quantity. So we can treat the depth and height and strength of these updraft and downdraft cycles as being uncertain parameters that we're going to be using within the MCMC framework. And then finally, how do we map the modeled ice crystals to the radar variables? And this in itself has been an entire breakout session at the ASR before, talking about these things called forward operators. How do you go from the model space to the observational space? So these particle property models typically simulate ice particles as spheroids. In this case, I've shown like an oblate spheroid. It would be representative of, say, a dendrite. And they have just some effective density that's associated with them. But it turns out that given the size, shape, and effective density for what's being produced by these particle property models, those are insufficient to characterize the electromagnetic scattering from radar. And so what needs to be done is basically accounting for that uncertainty. And so Robert Schromm, as part of his PhD work, came up with a probabilistic way to treat this, where given the output from the particle property model, so size, aspect ratio, and effective density, he could analytically create all of these different myriad shapes of snow crystals with various types of branches and branch thicknesses. And the idea is that all of these different shapes are going to affect the way that we map between the modeled output and the radar scattering. So it accounts for that uncertainty in this probabilistic way. Okay, so are we up for the task? Can we take all of these things and try to track all of these different sources of uncertainty within the MCMC framework and see what happens? So here's an example from that Arctic case that we showed before. The blue vertical profiles and error bars here represent the Kaiser radar observations, so the vertically pointing radar observations. It gives us reflectivity and fall speed. And then the X-Sapper radar observations are shown in yellow, and the uncertainty bounds there as the error bars. And these are both just taken from those images I showed earlier. And then the MCMC runs, many runs using that simplified modeling framework are shown by these white lines. So you can kind of see that they do span pretty well the reflectivity profile, the ZDR profile, and the fall speed or mean Doppler velocity profile here. So that's great, but it's kind of easy actually to match the observations. You can tune things around. What we really want to know is how well is this actually getting the underlying physics? And for that, we can look at how the model is predicting these. In this case, we have this depicted as these deposition coefficients, but the idea is that this is based on the laboratory measurements. And these are this sort of parameterization for how the shape of the crystals evolves. And so only using those radar observations, we actually end up something like this in the temperature range in which we looked. So the estimates obtained from the YARM radar observations actually did a pretty good job at falling within the range of those independent laboratory measurements. In addition, we have these sort of very busy plots that we call the corner plots. But basically, they're showing all of these uncertain parameter PDFs and they're joint PDFs. So the uncertain parameters are listed along the axes. And again, these are both associated with the microphysical model, with the dynamic model, and with that radar forward model. Along the edge here, the diagonal, these are the marginal PDFs, and you can kind of see those like that. And then each one of these individual panels shows a joint PDF between each uncertain parameter. So we'll just kind of zoom in real quick and look at this one in particular. And these two parameters represent the one that governs the development of those ice crystal habits or the ice crystal shapes. And then the one on the vertical axis here is the ice particle number concentration, which we also treated as an uncertain parameter. And what you can see is that the fact that these are not, even though the priors are uniform, the fact that the posteriors have these sort of nice looking Gaussian-ish kind of PDFs implies that there's some constraint being provided by the radar observations. Further, we see that there's a correlation between these parameters. Which implies that if we make additional measurements that can somehow constrain one, we might actually provide information about the other. So to conclude, since I'm running short on time, we basically demonstrated that Doppler polarimetric radars can provide useful quantitative constraint for these uncertain model parameters. And And these, the framework does produce parameter PDFs that captures a realistic mode of microphysical variability for vapor growth. I'll mention that we are working on aggregation currently with similar data from the Arctic, and we do see an additional constraint for certain aggregation parameters. So there's some optimism for that as well for other microphysical processes. And then finally, the robust uncertainty estimates that we've came up with here demonstrates that where we need additional constraining observations. And in terms of what we can use, the fully polarimetric K-band radar up in the north slope of Alaska now for ARM is providing some additional quantities that we haven't considered yet that do provide some additional information, independent information we hope to use. So with that, I will end, and if there's any time for questions, I'll take them. Otherwise, I can talk in the chat with everyone afterwards. Thank you.
Thank you, Matt, for a really nice talk. Let's take time for one question. And so there was a question and a related question in the chat here. How do you limit it to these types of crystals, and how do you know you have the right distribution of crystal types?
Ah, great questions. Okay, so in the one case when we looked for vapor growth only, there were some very limited ground observations that did show, they had photographs of these kind of branched planar crystals. So based on that, plus the radar observations for that kind of narrow time period in space, we were pretty confident that what we were seeing was just vapor depositional growth predominantly with very limited rhyming and aggregation. And then how do we know that we have a good estimate or good variability of those crystal shapes? Those were all sort of developed by Robert Schromm, based sort of on photographs, but obviously it does not span the full variety of nature. And he can kind of play around with those different parameters and do whatever we want. So ultimately we were hoping to use some sort of computer vision or some sort of machine learning based on photographs, but we just need a large number of those photographs to train it on.